Thank you, Ray. Appreciate the opportunity to be part of this marathon. I want to get it into presentation mode, so hopefully, can you see it now?
Yep.
Okay, wonderful. So I'm going to talk to you today about.
Wait, we're not in presentation mode, Louis.
We are not. Okay, what do you see right now?
We see just the PowerPoint.
See the PowerPoint. You don't see
on the
okay,
slide at the bottom.
Stop share.
Oh,
Please. I'm going to try again.
all right. We see the, you just have to get into presentation mode. Yeah.
Right.
Yep.
Now, what do you see?
Wait a minute.
Wait a minute.
You know, patience is not my best virtue, but I'm trying. So do you see the first slide or not?
We do. Just keep going. It's fine. Yeah.
Okay. What do you see? The title page or?
Yeah, we see a whole PowerPoint setup. So we have the other slides to the left as well.
Okay. Yeah, I apologize for that. I don't know what's going on wrong, but I don't want to encroach on somebody else's time here. So the outline of my discussion today is I want to review the various biotechnologies as we can use it for municipal odor control. Look at what's a biofilter, a bioscrubber, and a biotrickling filter, because there's quite a few misnomers in the market, and I just want to try to get us all on the same basis. Then we will look at what are municipal odors and some of the myths and facts associated with biological odor control. In a large concrete tank or a container, or it can be a fiberglass container. They have wood chips in it, or it can be inorganic media type biofilters. There's various types available. Biofilters get designed around 45 seconds empty bed residence time, EBRT, although it can be as low as 20 for some applications and as high as more than 60 seconds. So they normally take quite a bit of footprint up at a plant. So if you have a landlocked plant, it becomes quite challenging to fit a biofilter. Organic odors like hydrogen sulfide, potentially some ammonia, and then also for your reduced organic sulfur compounds like mercaptan, dimethyl sulfide, and so on. The next technology is bioscrubbers. Bioscrubbers are normally a vertical tower arrangement with different trays on the inside. They normally use random media like polyurethane foam tube type media in the reactor. In bioscrubbers normally have a recirculation pump where you recirculate the irrigation liquid from the bottom of the reactor to the top, because a large portion of the biomass actually resides in the recirculation liquid. Bioscrubbers work very effective for the removal of hydrogen sulfide and be designed around the empty bed residence time of around 15 seconds as a rule of thumb.
I'm sorry, Louis.
Yes?
It's just me, or for me, the slides are not advanced. I still see your slide.
Probably the 10,000 miles between us.
There we go. That's right.
Can you see,
yes.
What do you see at the moment?
Now I see the biotrickling filter slide.
All right, so I'm just gonna, unfortunately, I'm gonna go the informal way. So here's the biotrickling filter slide. So this is the bioscrubber, by the way, for those that couldn't see it, and there's your biofilter that I started off with. And if I jump back to the biotrickling filters, they normally use structured synthetic media, and you have different media modules on the inside of the reactor, and they can actually remove both inorganic and organic odors. And when I say inorganic, I'm referring to hydrogen sulfide as ammonia, typically for municipal applications. And then obviously reduced organic sulfur compounds we all know as mercaptan, dimethyl sulfide, dimethyl disulfide, and so on. in 20 seconds, depending on the application. Now, just a little bit about chemistry. When you deal with biological odor control, there's two main groups of bacteria that is involved. You have your autotrophic bacteria that's do the oxidation of your hydrogen sulfide to sulfuric acid. The key thing is you don't want to stop at the intermediary sulfur because then you will plug up your reactor. So you want to get full oxidation to sulfuric acid. So that's why the drain water pH is typically around 2. In the arid regions, you can go as low as 1.7, just for water conservation. And you have different bacillus and hypermicrobium, and we've done a lot of molecular probe type technology to do these identifications. So that's a topic for a different time. But the beautiful thing is the bacteria can operate under a very low pH. And then the other group of bacteria that you're looking at, heterotrophs are responsible for the oxidation of your reduced organic sulfur compounds to CO2, or if you, for example, in the oil and gas industry, you have benzene, toluene, and so on, we refer to it normally as VOCs, but I know VOC. The term VOC has different meanings depending on where you are in the world. But that also gets oxidized to CO2, but totally different bacterial species. You have bacteria like Pseudomonas, and you have some fungi that's actually doing the work for you. But they're very sensitive to pH. So under low pH conditions, they don't function well, or they may actually die. Now, this slide shows you the key difference between a biotreatment filter and a bioscrubber, because I see in the industry that we use these terms interchangeably, and it's actually not correct. If you look at the left slide, this gives you a schematic of a biotreatment filter where you have your odorless air coming in, it goes through the media, and then the clean air goes out. The irrigation liquid for a biotreatment filter typically goes through the reactor once. So you establish a pH gradient in your media, and you are able to grow your autotrophic bacteria in the bottom, oxidize your sulfuric acid and remove some of the ammonia. And then your heterotrophs is removing the organic odors in the top. And that's how you can get, let's call it, complete treatment in a biotreatment filter. If you look at the scrubber, normally they recirculate the water through the media. So there's a recirculation pump. That's an easy way to distinguish between a biotreatment filter and a bioscrubber. And because the drain water is normally acidic, it's typically around 2, as I indicated earlier. When you recirculate acidic water, you acidify the whole media bed. And because of that, you are able to remove hydrogen sulfide. So if the specification is focused only on H2S, you're going to remove it, but you may still have an odor issue with the mercaptans and the DMS. Typically, you need a second stage polishing in order to get total odor control. And again, this is not my definition of the two. You can go to the WEF manual of practice 25 to learn more about it. So when we deal with municipal applications, and this schematic shows you just a typical wastewater treatment plant. The intent of this slide is to show you how the concentration and the composition of the air varies depending on where you are at a treatment plant. So if you're at the headworks area, you will find that the composition is mostly H2S, is hydrogen sulfide dominant, of reduced organic sulfate compounds. But as you go through the treatment plant, let's say the primary clarifier, the aerobic system, your H2S will go down, and the organic odors will be reasonably, reasonable 0.5, 1.5 parts per million. But when you get to sludge treatment, you will find that there's more ammonia and higher levels of reduced organic sulfur compounds, and not so much H2S, unless you have primary sludge that's mixed in, and you may get it. So what's the composition of the air, where you are at the treatment plant, and then you can select the proper biotechnology for the application. That's all. Now, what are some of the myths and facts around biotreatment filters or biotech? History is that biotreatment filters can only be used for hydrogen sulfide removal. And that is not true. If you look at the explanation I just gave earlier, because of the great diversity of microflora in the reactor, where you have your autotrophs and heterotrophs in the reactor, you are able to pretty much use biotreatment filters from a headworks to a sludge treatment area. And you just have to design it properly and know what the compounds are you're trying to remove. And for example, there's an installation in Florida where we had to give guarantees of metal mercaptan in addition to hydrogen sulfide and some other compounds. And in this particular application, they had 5 parts per million of mercaptan in the air. And you basically remove it to non-detect with a biotreatment filter. But they did not fully believe that it could be done. So they put a backup carbon system there with a bypass damper on the top, just in case it didn't meet the performance requirements. But over time, people start to believe the reliability of technology and that it actually can, in fact, be done. Another myth is that you need polishing, typically with a biotechnology. And again, it really depends on the technology that you use before you can make that statement and generalize. Because if you use a well-designed biotreatment filter, for example, and because of the mixed microflora, you are able to remove both the H2S and the reduced organic sulfur compounds in the same reactor. Whereas if you have a bioscrubber that's only designed for H2S, then you may need a second stage polishing. And that's why it's so important when you write specifications, you really need to not just look at H2S, but you need to look at total odor control. And in the US, actually, the engineers do a pretty good job in terms of defining it in terms of Odour Unit measurement requirements. But if we are in the Middle East, for example, the focus is heavily on hydrogen sulfide. And that's why they may still have problems that they experience from time to time. And this is the reason why you, from a H2S measurement perspective, you pass performance, but there may still be an odor. And now you understand why you have an odor. Here's, for example, an application at a sludge treatment facility at Mount Holly, New Jersey, where we have a biotreatment filter installed, 3,300 dilutions threshold going in, less than 300 going out. And frankly, as Scott said earlier, you know, most of the plants have very low detection thresholds that they want to meet on the fence line. Typically 5 odor units is very common in the US. And if you do dispersion modeling, you will find obviously at 300 dilutions to threshold and a significant distance from the fence line, you can demonstrate that dispersion modeling 5 odor units will not be a problem. Another myth is that bioscrubbers and biotreatment filters uses, or bioscrubbers uses less water than biotreatment filters. And again, that is not true. If you have the same application and you have the same airflow, same hydrogen sulfide concentration, same groundwater pH that you are operating at, then a bioscrubber and a biotreatment filter will use the same amount of water. And if you have installations or deal with biotechnology in the arid regions, like in Saudi Arabia, where water is very scarce, then it's sometimes at a lower pH just to conserve water. And frankly, the evidence is a simple mass balance, a sulfur mass balance. If you do a sulfur mass balance over a biotreatment filter, you look at what's the sulfur coming in, what's going out in the rainwater, in the air, and you do the same comparison with a bioscrubber on the right, then you will understand why I'm saying that the water use is actually the same for both technologies. Biotechnology is also, it's very versatile. You can use it in many different climates. You can use it in the cold climates that in the northern part of Canada. You can use it in the Middle East environment. The key thing is in cold climates, you just need to pay attention about, you know, with freeze protection so that you don't freeze at the water lines and all that. So yes, you may say that, Louis, how is that possible that you can use biotreatment filters or any type of biological technology in cold climates? And the reason is it is true that the activity is lower with colder temperatures than at warm temperatures, but in the colder climate, you will find that the concentrations of the compounds are also much lower in the winter time because the bioactivity in your sewer lines is also lower, and therefore they cannot compensate for each other. However, if you deal with an industrial application where the concentration year-round may stay the same, then you need to make special provision for heating stream just to keep the bioactivity in the reactor high enough to oxidize all the compounds. And then the other key factor is that media matters. You know, very often I almost want to say that engineers want to specify technologies by dictating a residence time and just use all media the same. And that is not correct because in the end of the day, if you have a random synthetic media versus a structured media, the design conditions for those applications or media types are very different. And you can actually get away with a much shorter empty bed residence time or a more compact design if you allow the technology provider to just meet the performance that's specified. So media matters. You can actually, in a well-designed biotechnology filter with structured media, get away with much shorter residence time for the same level of performance. So in conclusion, biotechnology is actually very versatile. It can be used for most odor control applications at treatment plants. I would think, for example, the only place where we may not recommend it is for high ammonia applications. And then you may just use acid scrubber, but besides that, most of the other applications are actually well suited for biotechnology. Key benefits, obviously, of biotechnology is low carbon footprint, very low OPEX. Scott talked about OPEX, and if you use chemicals, it costs a lot of money. You can have a long media life depending on what you select, and it's a sustainable, environmentally friendly technology. So with that, Ethan, thank you. Here, if there's any questions, I'll be happy to answer if there's time.
Thank you. We do actually have some questions. And I have to... one question is if in biotechnical filter media is biotechnical filter media selection critical to ensuring biomass accumulation is not excessive in high H2S concentration applications?
Yes, it's important that you have to look at loading when you design your systems as well. So if you, for example, if you deal in the Middle East environments where you can often get concentrations up to 1,000 parts per million plus, so it's actually very lethal. There you need to focus on your mass loading more than just the simple EVRT that you see in the US. So yes, you need to pay attention to mass loading to make sure that you don't have excessive growth and can potentially run the risk of plugging up your media.
One more. Thank you. One more question. Would bioscrubbers be more applicable for industrial applications and biogas treatment?
That is possible. In biogas treatment, the focus is obviously mostly on H2S and sometimes siloxane, but you cannot, to my knowledge, remove siloxane biologically. So you can use bioscrubbers for biogas treatment, but there you need to also, most biological biogas systems, desulfurization systems have a problem with sulfur plug up. So eventually you need to stop the whole process, clean out the reactor, clean the media, and then restart it because of actually this formula that I just showed here. Because biogas has a lack of oxygen, so you need to add oxygen to the biogas stream that's stoichiometrically sufficient to get a level of oxidation. And typically the bacteria will stop at sulfur and not take it fully to sulfate. So you still need to basically stop the process at some point, clean the media, and then restart it.
Yeah. Okay, cool. Well, thank you, Louis.
You're very welcome. Thank you, guys. It was fun.